topic is the high performance concrete and the advancements, ultrafine materials and their application in modern construction. So high performance concrete, most of my previous speakers have been able to properly, define it. I thought I would be the first person, but the definition has been done very well. So I would just move ahead. I would skip this. Now, what are the advantages? The first advantage that is very close to my heart is the better strength to weight ratio. Now, what I mean by strength to weight ratio is, a year back, some engineering college students, they were given a project. It was a competition across all engineering colleges in Maharashtra, and the challenge in front of the students was to get a strength of their concrete cubes in such a way that their strength is the highest compared to the weight of the cube. And this is the most basic challenge that any structural designer faces while designing any structure. It can be not just building, but even for the aeroplanes or ships, whatever. So the biggest challenge is the strength to weight ratio. And we took a plunge since they had come to us. We said, let us not design for the lowest weight to strength, but let us try to make highest strength weight. What I mean is not design a lightweight concrete, but to design a very high possible strength of concrete. And as luck had it, the team which we were supporting, they made the highest, they made the first rank because obviously the highest strength of concrete, the strength keeps on increasing, but the weight of concrete does not increase to that extent. It is not proportionate. So when the strength of concrete increases, the weight does not increase, the density does not increase proportionately. The best advantage that I feel with high performance concrete is strength to weight. And also, as Mr. Manish had told, it's not just about high strength. It's about all the other parameters which normal conventional concretes are not able to achieve. Like it could be high, durability. It could be high modulus of elasticity. And most of the times that we have seen is when we try to achieve those other parameters apart from strength for high performance, like high modulus of elasticity or high durability, irrespective of the grade of concrete, we somehow end up getting a higher strength. It requires kind of lot of modeling and all that. But despite modeling or trying to optimize at whatever possible way, if we end up getting high strength concrete. Only one or two cases like concrete for freezing and thawing conditions where you want air bubbles inside or air voids inside the concrete. Apart from that, any other place, we feel that we have seen that the high durability or high performance ends up in getting high strength of concrete. So the second aspect of this high performance concrete is you start getting higher strength concrete, okay, because of lower water cement ratio. Now, apart from this, it is also economical. If you see the application of high performance concrete, it is normally for a city like Mumbai, it would be used for a high-rise building where most of the village population is moving towards the cities for better living, better way of living, and low cost of whatever you call it. So when the city is getting concentrated with more and more number of people, it becomes kind of difficult to squeeze in more and more people with no high-rise buildings. So if you see the places like Mumbai, Chennai, Delhi, they've now started moving towards high-rise buildings where more and more people are now occupying the land, the same amount of land. So it becomes kind of very economical to the entire nation when the entire population is moving closer and closer. Like for example, it would be much cheaper for a state if the same building has got the office and the residence of the same person. So all he has to do is he has to, instead of traveling from one part of city, maybe say from Thane to Churchgate, if he can stay in the same building, and that is possible only if we have got such kind of arrangements in planning. The answer for such problems lies in high performance concrete. Now, what are the challenges? After talking about the advantages, um, the real problem comes in or when you start manufacturing high performance concrete. As I was saying, that high performance concrete usually ends up in getting high strength concrete, and most of the high performance concretes have a very low water cement ratio. Now, when this low water cement ratio is there, it leads to a very high viscosity in concrete, leading to very high problems of pumping pressure. The pumping of concrete becomes a big challenge. And to get the required strength, you have to reduce the water cement ratio. If you see the old mixed design code 10262 had got 5 graphs, A, B, C, D, E, F, 6 graphs, and for the same water cement ratio, a higher strength cement would require a higher water cement ratio to get the same strength as compared to a cement which has got lower strength. Naturally, what would happen is a high strength cement would end up giving the same strength with very low cement content or a higher water cement ratio. Now, this is the challenge. Earlier when we did not have requirement of so huge quantum of high strength concrete, that time we did not have the problems of pumping to a high-rise tower or also very viscous concrete. But today, what has happened is since the demand is increasing for high performance concrete, we are again and again facing challenges because the water cement ratio is very low. So we need something where you get high strength despite high water cement ratio to get the required pumping ability and lesser friction or lesser viscous forces. And also we require something where you get the consistent performance of the mix despite the variation, the natural variation that happens in the strength of cement, the strength of aggregates. And also it needs to be economical. The solution that is there, it needs to be economical. And one challenge that we always keep on facing is for high-rise buildings, the structure sizes are much higher. So this bullet train, we were involved in certain sections of the bullet train, and we came across many challenges that they were facing. One was, despite no part of the designers tried, the girders that they have got, certain portions of girder qualify to become mass concrete, where the heat of hydration is very high and it was leading to cracks. Now, this was happening because of very high cement content and leading to very high, heat of hydration and then cracking or other problems. So this is also one of the challenges that is being faced in high performance concrete. And I said the high cost because you need to have very high amount of cement because of requirement of very low water cement ratio and also because of high workability. Now, these are the challenges. Now, how can ultrafine material resolve these problems? Basically, the reason why cement gives you lower strength is for that you need to understand when cement was first manufactured, it was not of that much strength that it is that we get today. So today we are getting a strength of 61 MPa, as per the standard testing method, 61, 63. But when the cement production first started, when we started first using this modern cement, it was by batch process and the fineness was not that high. The strength that came to India first was 33 MPa, 33 grade cement. Now, the reason was the grinding was not that fine. The chemical properties were not that much optimized. The chemical contents were not that much optimized. So that led to lower strength. And also because there were no admixtures that time, so we had to use a higher water content for the same cement content, and we ended up getting very low strengths than what was a potentially possible strength. So the reason that happens is because at a higher water cement ratio, the cement particles are very far away from each other. If you see the right side picture, it is it's a model which shows a typical concrete which has got a very high water cement ratio, whereas on the left hand side it's a high strength concrete with a very low water cement ratio. Too much cement, very high amount of cement, but very less water. Now when you move This is the traditional method, right from right to left when you move. This is the traditional method of increasing the strength. Now, what happens with ultrafine minerals is it is able to go inside the pores. Okay, it is able to block these big pores, which are called capillary pores, and also hydrate. These are nothing but these are fly ash or GGBFS or microsilica particles, and they lead to better hydration of cement, higher, faster reaction, and much more higher strength as compared to just the cement. So you are able to get the same strength at a higher water cement ratio and a better workability. So this is a model that I've tried to create. It was very difficult to make, but it was cement. What I'm just trying to tell is when the cement hydrates, the cement actually first starts dissolving in water. And if you see the particle which is coming out, that is nothing but the calcium ions, the silicate ions, CS ions, and they hydrate and they form CSH gel in the water. They do not form it on the surface of the cement. So the biggest challenge that comes in front of the designers is when this CSH gel, the material which gives strength to the concrete, it has to precipitate on a hard surface. So the only surface that it finds is the cement particle, and then it keeps on, precipitating on the cement surface. Thereby, what happens is after some time, the cement particle is not able to hydrate because it is getting covered with CSH. Now, when we have got ultrafine materials, we have been able to find certain materials which act like nucleation sites. So what happens is the CSH gel, instead of precipitating on the cement particle, it precipitates on the ultrafine particle. And this way, there is more and more CSH being formed, at early age, and you are able to get a higher strength. So this is exactly what I've trying to tell. So ultrafine materials are mostly 10 to 100 times smaller than cement particle with a very high surface area. It has got it gives you good durability and engineering properties. First, because they are SCMs, supplementary cementitious materials, which are not non-calcareous, mostly GGBFS or fly ash or silica-based microsilica. And also you are able to reduce the cost by reducing the cement content. If you design it carefully, you will be able to reduce the cost of concrete, and also since you're able to reduce the cement, you're also able to reduce the heat of hydration, all the properties, all the challenges that are associated with cement. And obviously one of them is the shrinkage of cement after hydration. That is it from my side. Thank you again.